I'm TaiNing from National University of Singapore. I'm going to present this paper, Improving Joint Reorderability with Compensation Operators. The problem is joint reordering. Inner joints are associative and commutative, so it's easier to reorder inner joints. The challenge is when we have outer joints or anti-joints in the query, because they are in general not associative or commutative. Here, for example, left outer joint and anti-joint are not associative, so it's not equal. We use arrow to denote left outer joint and triangle to denote anti-joint. The goal of this paper is to improve the joint reorderability for outer joint and anti-joint queries. This paper introduces a compensation-based approach that supports complete joint reorderability for inner joints, one-sided outer joint, and anti-joint. We introduced two new compensation operators and a new plan generation algorithm. The experiments show that the performance gain by our approach is up to 2.8 for this 5-table query. This is a conventional plan. This is a plan generated by our approach with compensations above the joints. If we don't use compensations, it is impossible to reorder to join R1 and R2 first in this case. There are two state-of-the-art approaches for joint reordering. The first is a transformation-based approach. TPA supports all valid transformations. For example, left outer joint and left outer joint are associative in nature, so it's a valid transformation. Left outer joint and anti-joint are not associative, so it's an invalid transformation and is not supported by TPA. The second is a compensation-based approach. CPA tries to compensate for invalid joint reordering. It supports all inner joint and one-sided outer joint. For example, left outer joint and anti-joint are not associative, but if we add in the lambda and beta compensation operators, we could actually reorder to join R1 and R2 first. So as you can see, existing approaches only support very limited joint reordering, and in particular, anti-joints are quite poorly supported. So our goal is to support more joint reordering than TPA and CPA, and the eventual goal is to support all possible joint reordering given a joint query. Our approach is also compensation-based, similar to CPA. CPA handles inner joint and one-sided outer joint by introducing two compensation operators, lambda and beta. So the motivation of our paper is we want to introduce some new compensation operator that can handle anti-joint and can achieve more joint reordering. In CPA, it always rewrites inner joint and one-sided outer joint into cross product followed by compensation. So reordering of joints now becomes reordering of compensations. We want to do something similar. First, we also want to rewrite anti-joint to cross product or inner joint left outer joint because we already have ways to handle inner joint or left outer joint. Second, I hope the new compensation operators can be reordered with other compensations and joints as much as possible. Third, after swapping two joint operators, I want to pull up the compensations so that further joint reorderings are enabled. I introduced two new compensation operators, gamma and gamma star. Gamma is simply removing tuples whose attributes in A are not null. Gamma star is similar to gamma. It also keeps attributes in gamma R1. And for the attributes not in gamma R1, it will nullify all the attributes except for attributes in B. Here, the red tuples have non-null attributes in A, so gamma will remove the red tuples, while gamma star will nullify the red tuples except for attributes in B. With these two new compensation operators, first I could handle anti-joint by rewriting to left outer joint followed by gamma. Then for 2 and 3, we have derived a complete set of rewriting rules. These are the rewriting rules for pulling gamma and gamma star above joint operators. These are the rules for swapping any two joint operators. With these rewriting rules, we achieve complete joint reorderability for anti-joint, one-sided outer joint, and inner joint. Our second contribution is we introduce a new top-down plan enumeration algorithm that can do code space pruning and subplan reuse. So why the traditional bottom-up approach doesn't work? Because bottom-up enumeration assumes that subplans with the same set of relations always compute the same result. But if we have compensations in the plan, and if the compensations have been put out, then subplans may become non-equivalent. So we need a new plan generation algorithm. The details can be found in the paper. For implementation of compensation operators, there are two choices. First is a language-based approach. It is less intrusive and easier to implement, so in this paper we focus on this approach. All the compensation operators used can be implemented on SQL level. Then the second possibility is to do a native implementation of all the compensation operators, and it is part of our future work. I will show some experimental results. We compare against Postgres using TPCH dataset. I will use this query as an example. Here is the plan chosen by Postgres, and here is the plan that could be produced by our approach with compensations above the join operators. Here are the runtime results. So the x-axis is the selectivity factor for the anti-join between R1 and R2. When we have a large selectivity factor, we have large anti-join result, which means many R1 tuples do not join with R2. So over here in our plan, we will have a small intermediate result here. So our plan will be better than Postgres plan. Yeah. So if I increase the data size, the improvement factor also increases. For 100 gigabyte database, the factor is up to 2.8. I have talked about the join reordering approach, the plan enumeration, and some experimental results. For future work, first we want to do optimized native implementation of the compensations in a query optimizer. Second, we want to work on a bottom-up plan enumeration algorithm because right now we only have a top-down solution. Third, we try to achieve complete join reorderability also for queries with full outer join. Thank you. Any questions?
So you use the dataset of the TPCH benchmark.
Yes.
How many queries are there? How many queries are there among TPCH benchmarks? 23 among 23 queries. How many queries contains outer joins or anti-join?
Actually, we use a data set, but we don't use a query set because we want large join queries, like 5 table queries, 4 table queries. But in TPCH, there are only a few join queries and really not so large table numbers. We just use the data set and we manually try different join queries